Hello, this is Chen Li from University of Science and Technology of China. Today, actually, I'm going to present our recent work. This work is about towards cost-effective and elastic cloud database deployment while memory disaggregation. So let's begin with this introduction to this cost-effective and elastic cloud native database. So what are the cloud native database? The cloud native database are right now actually receive increasing attention. They are the database that can leverage modern cloud infrastructures, for example, like Amazon AWS, like Azure, like even like a Google Cloud, and so on and so forth. Their target actually high performance, high elasticity in terms of the resource provision and the low price. And also, because of the rapid development, right now the cloud native databases have been served as the building block for cloud applications. So there are a bunch of these cloud native databases, for example, like Aurora from Amazon, like ProDB from Alibaba, and also the Spanner from Google, and so on and so forth. So with the rise of the cloud native database, we have some fine-grained measurement and to identify the elastic resources demands from these cloud native databases. For example, we measured um, a week of the resource utilization, in particular the CPU utilization. So here the figures show that most of the time, actually the CPU utilization is below 50%. However, for some short period of time, the variance is so high. For example, the CPU utilization can reach up to more than 90% at the peak. So with this kind of resource variance, actually, the traditional monolithic setup, for example, like the resource provisioning, cannot meet these dynamic demands. So what the way out? So since it's just because of this high speed network, for example, like the RDMA, like the IB network, which give you ultra low latency and also really high like bandwidth. So there is a new direction called resource disaggregation. So what is this resource disaggregation? In, so actually compared to this monolithic setup where the resource allocation is as within a machine boundary, right? So this resource disaggregation allow the CPU, memory, and storage, they are connected as network. So the software can be split and run in multiple places and treat these networked devices as a computer. So for example, there are two main directions. One is called a disaggregated database. For example, the representative examples are Aurora and PaloDB. They're both published at Sigmod in different layers. What their focus is, they focus on compute and storage disaggregation. For instance, they push the storage, like the database storage, to the network connected component. In addition to this kind of a disaggregated database, there are some other approach which we call the general disaggregation approaches. The representative examples are localOS, published at OSDI 18, and Infinite Swap. It's the infinite swap server. What they're doing there is that they implement this kind of resource disaggregation ability in this kernel, which can be transparent to the application. So, however, this kind of general disaggregation approach suffer from high memory access overhead and high failure recovery overhead. That's because of their beliefs to database I/O characteristics. That's because they're general. This is the price they should pay, and they often go through the traditional I/O stack. Next, we will use some examples and data to illustrate these two fronts, the high memory access latency and the failure recovery latency. Um, so what we did there is that we run some workloads, for example, like the very traditional and the very representative the workload like TPCC and TPCH. TPCC is the OLTP workload and TPCH is actually OLAP workloads. Um, And we run the workloads with the infinite swap is one of the baseline we can find, which offer resource disaggregation. And we maintain a remote memory pool, which can actually can offload part of the cached data from local to remote, and to alleviate this memory space problem. And the remote memory pool is accessed via this 25 Gbps network with RDMA enabled, which can be really fast. So here on the left-hand side, you will see TPCC the performance. We changed the local buffer size from 100% of the whole data size and decreased to the 50%. And once you actually we observed that from this pattern is if you decrease the local buffer size ratio, which will result in a significant drop in performance. For example, when you reach the reduce to 50%, you get half the performance of the original one, right? That's the price that you should pay because of the fast, because of the remote access. And the second thing is that actually, once you look into the TPCH results, we just choose the three queries, query 3, query 12, query 15. And the similar trend we observed as a TPCC, and even this performance drop is more severe, right? So the first takeaway point is that uh, even we have this fast memory access like remote one, but it's still not enough, right? So this general disaggregation stuff will add a lot of overhead along the access path. Therefore, we need the co-design of the database kernel and the memory disaggregation. This is the first challenge, right? So the second challenge we found is this fault recovery cost. As everybody know that the fault tolerance is very important for database applications, right? Once you write data, you need to make sure that the data will not be lost if you get an acknowledgement back. Um, so we test this fault recovery cost by running MySQL to deploy a real world application on top of Infinite Swap. And then, part of the data will be local and the part of the data will cached remotely. And if we have this remote access, we might have this resource performance drop, right? We run the TPCC workload and we also change the remote memory ratios. And in addition, we actually injected crashes during the experiment, and we crashed the MySQL instance and measured the failover time costs. So here the figure shows that the from the MySQL and to uh, these two bars in the middle is actually we use the infinite swap, right? And to decrease the number of the amount of the memory we use locally. And the final bar is actually represents the work we're going to propose called the local base, right? So if we look at the MySQL part, actually the recovery take a really long time, right? The warm up take another half time. And once we move to this infinite swap where we leverage remote buffer, actually we found that the recovery part is remain the same, but the warm up takes so long. The problem is that the page cached remotely are no longer used or they just disappeared, right? So we cannot enable the faster recovery, even the local crash, but the remote is still alive. But if you move to this local base, actually, if this local crash, then we enable really fast recovery and also shorten the warm up period of time. The second takeaway point is that independent fault handling require us to bridge the gap between the monolithic fault tolerance protocol and the memory disaggregation. That's implied that if we want to leverage this memory disaggregation, uh, we not only we not only need to actually distribute the hardware, but also we need to sort of distribute the software as well. So we need to make some innovations to the traditional database kernel or stack. What we did there is that we proposed database and memory disaggregation co-design solution. At a very high level, actually, uh, so for example, in the figure we show is the high big picture of the local base, which is the cloud native database which in which support or embedded embody the memory disaggregation. So we have a compute node. Actually, this is normally run the MySQL instance, like the traditional database kernel. But actually, we inject some code inside it to manage the remote memory as well. And at the remote side, actually, we have this global memory cluster consists of many uh, physical servers, and they harvest the memory from these servers and form the remote buffer pool. And also we have this allocator. And at the bottom side, we have the persistent shared storage, which is still guarantee the uh, fault tolerance. For example, we can still ensure crash consistency because of this layer. The beauty of this setup is that we bypass OS kernel uh, completely. So we do not actually implement this disaggregation as this influx swap that we provide the general one. So instead, actually, we directly talk to the remote side from the database kernel. And we use RDMA, heavily use RDMA. In particular, we use this high performance one-sided RDMA. And we return the MySQL sophisticated optimizations such as LRU, right? This LRU to manage the cached blocks or pages. And we also leverage the database access patterns and the data layout for further optimization. So let's zoom in each part and understand how it works. So first we have this local and remote memory management. First, in the local side, actually, we use two-level RRU. One level is managed this is called LRU LBP, is managed the cache the data locally. Another one is called LRU RBP, is actually managed the all the pages actually remote cached. So for one page, actually, it could be possible that it has the remote cached copy and also local cached copy as well. So this two-level LRU will hold all this metadata of the local and remotely cached page, and also reduce the communication with the remote memory node because we don't need to read the metadata anymore. So locally, we can decide the address of the remote pages as well. Um, and once we have this kind of a memory management, and from the SQL execution engine, then we need to read the data, right? So if so, the very easy way, the easiest way is that the page is in the local buffer, for example, just like the arrow indicates, right? So then we just return from this local buffer. So there is so easy, right? However, if this page is not locally cached but is remote cached, so we can look up into this LRU list and get okay remote site. Then we can use this remote memory address and to issue a one-sided RDMA to the remote side and fetch the data from remote, and then we populate its local RRU to manage it. And if the page is not cached, either in the local buffer and the remote buffer, we need to read it from the persistent storage. How it works? So our local instance will read from the persistent shared storage and first registered put into the LRU LBP, the local LRU, and also we will claim or request a page from the remote side and get a page allocated for this cached page, and then we also modify this RU remote buffer pool, then actually we can manage this page as well. Um, so another thing actually I want to talk more about is actually the new fault tolerance protocol actually we introduced. As I mentioned before, um, so the traditional general disaggregation solution like the infinite swap suffer a lot from this high fault tolerance cost, right? So here actually we propose that we need to co-design the fault tolerance protocol with this disaggregation. In particularly that we need to split the fault tolerance into multiple pieces. So here actually we introduce two-tier ARIS protocol. The first tier actually we created the two-tier checkpoints actually summarize the status of the database, right? So the tier one checkpoints actually is handled like this, right? So the compute node where the MySQL runs flash the fine-grained checkpoints to the remote buffer at high speed via RDMA. That is okay because the checkpoints is just like soft checkpoints. And tier 2 checkpoints are more important because it's where affect the fault tolerance level. So actually, we let the remote memory node actually flash the big giant checkpoints to the storage as usual, just as the traditional application. Because we do not modify this login stuff, so these two-tier checkpoints will not introduce any wrong results or violation of the consistency. Okay, so with this two-tier protocol, how this transaction will work, in particular, write transaction works in our system. Okay, it works like this. The transaction manager first issue this transaction, like the comments to the cache the page, right? Assume that the page is locally cached. Otherwise, we fetch from remote or like the persistent storage system, persistent shared storage. And once the updates is done, it also write the log entry to the log buffer, and then it will append this the request to the flash list. So seeing that okay, there is the page is dirty, you need to flash uh, to reflect the new changes. And after this is done, um, so the compute node will reply to the upper layer, like the client or like the transaction manager, with the acknowledgement. Okay, this is done on the critical path. And in off from the critical path in the background. So this we have this lightweight fault tolerance demo running in this compute node. It's actually periodically check the flash LBP and get the list of the dirty pages that need to flash. And once it's identified, it's actually write the new data to the remote page because they are cached, right? And then they create a checkpoint and I write to the checkpoints and also add this the list of the dirty page to this flash list maintained by remote site. Okay, once the remote site have this flash list, it's actually we'll do the following, right? What we'll do is that there is the heavy fault tolerance demo run at the remote site. We'll also check the flash list, and once the flash list gets, it will write the data to the data area on the persist memory, persist shared storage, and also write the big checkpoints to the storage site. It's done. All these communications are heavily used RDMA, so it can be really fast. Okay, and finally, this heavy fault tolerance demo actually reply uh, to the actually the compute node, and also compute node will periodically purge this redo log. Right now we use redo log, right, to trunk the log to avoid that the log were increasing so fast. Okay, this is what we have done with this two-tier ARIS protocol. Okay, following that, I will show some result actually run from our intensive experiments. So we have this, we run the experiments on this on one machine. So actually on two actually machine with this Intel Xeon CPU, and each machine will have a 512 GB DDR4 DRAM, and also the machines are connected by 25 Gbps network, which will use Mellux Connect 84 with RDMA enabled. And we run the workloads, TPCC, TPCH, sysbench, and production workflows. And for TPCC, we populate database at 20 GB, and for TPCH, we populate database as 40 GB. So the baseline actually will compare to two. The first one is monolithic MySQL, which they do not use the resource disaggregation at all. And we also run MySQL over InfiniSwap to uh, act as a close baseline to exercise the resource disaggregation. So here we will see some results. So the first set of results I show is with the TPCC. We run TPCC and we increase the workload by increasing the number of threads. So here we present this throughput in terms of the TPMC, and also we we report the 99% of the latency in terms of microsecond. So here we use the MySQL 100 represent this monolithic setup where we do not use the remote buffer, right, at all. And then we compare the InfiniSwap, 75 75 and 50, which represent how much of data of the whole data set we cached locally, and the rest actually we cached remotely. And the similar setup we apply to the local base as our system. So here actually we compare to when the result actually highlights that compared to the monolithic MySQL setup, we have this infinite swap that's so the baseline actually get worse by up to 2 times in throughput compared to this monolithic the MySQL setup. And if we look into the latency, almost the same, right? Like the tail latency, it gets worsened by 2.35 times. However, our solution, local base, because of this heavily used RDMA and manage this remote buffer in a lightweight fashion, so Legabase actually brings only up to 3.8% loss in throughput. So which means that we achieve the comparable results as this MySQL local. Actually, but however, actually we bring a lot of data to cache remotely, right? Okay, this is a very nice result. So if we move to this TPCH, which is the analytics workload, right? We also observed the similar trend as we did for this TPCC. We again to deploy like MySQL with all local buffer, and also we deploy infinite swap in different memory setting. This memory represent how much we cached locally, similar to local base, right? So our conclusion is that even we offload a part of the data to the remote site, local base 75% the achieved latency as closer as to the one that achieved by the MySQL monolithic setup, right? And also for this other side, actually, the local base actually uh, we outperform MySQL over infinite swap, right? In many aspects. For example, we take this Q11, this query, as one example. We look into the detailed breaking down results. We found that the local base actually we achieve 75% faster lower latency than this MySQL over infinite swap, right? So that indicates that our disaggregated cloud database uh, not only fitting or can benefit the TPCC workloads like the OLTP workloads, but also can benefit this analytic workloads, which usually require demands for a large number of this memory consumption. So that is some feasible solution. Okay, so we also have some other results. Actually, if you are interested in, you can take a look in the paper. The paper is published at WellDB this year. So go on to check that with the title. Okay, so next I will show this. We claim that we will not only have this latency benefits, but also we can enable faster recovery, right, and shorter warm up time. So here, what we did there is that we deploy MySQL, this all local, and also we deploy local base, and then we crash so this light green line represents the we crash local sites, and actually another this black line represents local base. This represents that we crash the remote site as well. So we found that when all or remote memory crashes, local base this dark this black curve look very similar to this pinker purple curve, right? This means that local base resorts to the normal MySQL recovery process. So both actually they're the same, right? However, with the only local node crash, so look at this light green curve. Local base actually can reuse the vast majority of the remote pages, right? As long as they are not actually corrupted. So we can significantly reduce the state recovery and warm up time costs, right? So that's a very fantastic work. So you can see this the curve jumped back, which means it can resume from the crash, and the throughput will still run at a very high rate. Okay, finally, actually, we conclude that because of this very nice feature, so local base actually can benefit uh, efficient planned hardware reconfiguration. For example, we can move a Docker running MySQL from one machine to another because you only have the few item cached locally. It's almost stateless, right? This all we should thank to the RDMA connections. Okay, finally, I want to conclude here. Localbase is the novel memory disaggregated cloud native database architecture. So I hope that I convinced you with the support of the RDMA. Localbase is able to scale CPU and memory capacity independently with comparable performance as the monolithic setup. So this monolithic setup is not using remote memory at all. And finally, we believe that local base actually can achieve faster static recovery and is more cost-effective than state-of-art baselines, like the general resource disaggregation solutions. Okay, so I would like to wrap up my talk here. So if you're interested in, you can look up our papers. So here is my personal web page. If you are interested in, you can find my email and to write my email. Uh, so that's it. I would like to thank all for the invitation and so happy that I contribute to this community and we will have a lot of discussion offline. Thank you. Hope you enjoyed the meeting.